Hi, it's Tim. Welcome back to the corner. As I'm filming this, it's Christmas Eve. I have just finished filming the video on the Tynemouth Minstrel 4D kit build. If you haven't seen that, it's probably already on the channel, so check it up there. And I was thinking about what I was going to do next. You'll remember this, it's the PIEEE-1541. And we built this not very long ago on this channel. And this got me to thinking, there is an SD to, not IEC, but an SD to IEEE, or an SD to PET rather, device for the PET, which is this. And there are other ones similar to this. And it has a number of issues, I think. One is that this particular device has to be the only thing on the IEEE bus, and consequently you can't plug anything else in there. You can't plug in a real disk drive. It does, however, read D82 format files, and a D82 format file is an 8250 disk, so it's a 1 megabyte disk, quad density. As I've discovered when I've been trying to test my SFD 1001, you can't have this and an SFD at the same time. There is another device that you can plug in to an IEEE and it has a pass-through, and you can plug in other devices, but that doesn't read D82 files, so it's kind of a catch-22. This also doesn't read D82 files, but this has got a Raspberry Pi in it, and it occurred to me that one of these, a Raspberry Pi, could talk to an IEEE device just as easily as it could talk to an IEC device. So I was thinking, over the Christmas holiday, I have to learn Python for my day job, for work. And Python is a native language of the Raspberry Pi. So it's interpreted, which makes it a bit slow, but I could make an IEEE 488 device, a hat if you like, that runs on a Raspberry Pi, and program it in Python and have that as, I'm going to call it, a PIEEE 488 drive. Whether I'll get it to work or not, I don't know, but I'm going to have a go. I rather like that name, PIEEE 488. So yeah, that's what I'm thinking. That's what I'm thinking. So I will, or I would like to take it as far as a PCB at least, and maybe a 3D printed case. It'll be a wider case. My thought is to make it look a bit, this looks like a 1541. My thought for the IEEE device is to make it look like an 8250, a low profile 8250. So it's going to be yay wide, which would work with the Centronics style switches, buttons, I think. And I don't know how wide the PCB is going to be, but it's going to be a hat, so it's going to be at least as big as this. Anyhow, I'm waffling now, so yeah, let's do this. Once this project is up and running, I shall want to produce a PCB, and I shall turn to our sponsors, PCBWay. Starting from $5 for just 10 boards, PCBWay will produce quality printed circuit boards within 24 hours of receiving the order. And if you don't have your own design but you want something to build, then check out their shared projects. The Retro Stuffs category has got nearly 20 pages of projects for Commodore, for Amiga, for Atari, and other machines, all ready to go. Why not check them out? www.pcbway.com. This is an approximate sketch of what I want to do. So let's have over here the Pi's GPIO bus. Now there are 26 pins on that, or at least 26 GPIO pins, and some of them are specific purposes, but for now that's all we really need to worry about. Over here is the IEEE-488 bus, and what we need is basically two chips, and this one is a SN75160 and this is an SN75161, and this drives the data bus of the IEEE-488 port, and this drives the control port, the control bus of the IEEE port, and these of course are driven by D0 to D7, and this is going to be the control lines signals. So there are 8 of those, and I can list those out in no particular order. Okay, so that is the basics of the GPIO to IEEE-488, what I'm going to call the... And this gives us some pins left over to do things like switches and LEDs and stuff. But we also want to drive an OLED. And to drive the OLED, we need 2 specific pins. So we need... An OLED is driven by what is called an I2C bus. And that's basically, it's a serial bus. It has a data line and a clock line. And those are GPIO 2 and GPIO 3. So those are fixed. We need those to drive the OLED. So what I'm thinking, I want to make this a dual drive, so I'm going to have dual controls and dual OLEDs. So let's have, say, OLED 1 and OLED 2. Now, I2C devices are addressed by addresses, so that is going to be, I think, address 3C. And this we can have to make address 3D. The numbers may be different, I would have to go and check. This requires must be address configurable. So, because some of these OLED devices, and this is the same as the one on the PIEEE-1541, some of them are fixed addresses and you can't change it. But if you want 2 of them, then you have to change the address on one of them, and that usually involves soldering a link or something. Now, I also want a bunch of LEDs, so we're going to have 3 LEDs, and that's going to be drive 0 activity, that's going to be drive 1 activity, and that's going to be on /error. So just like a normal disk drive, if you screw something up, it will light up the error light. So maybe that's actually a, I don't know, 2 color. And we want a bunch of switches to control up, down, select, etc. Basically 3. And we have to find GPIO pins for those. Now, one thing that we can do is we can add a 23017 chip, and that is powered by 3.3 volts. I think these are powered by 5 volts. And that takes the I2C and it gives us 16 outputs. So this, again, it has an address on the I2C bus, and we can send data to that, and we can then program the LEDs and get information from the switches. So we're going to want, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those, and we have 8 spare connections if we use everything, including all the sort of reserved things. So I think we need one of those. That's available in 2 versions. There's I think it's going to be a 23008 or something. There's an 8 output version and a 16 output version. This is the 16 output version. It gives us plenty of spares and overheads and stuff that we can use if we want to later. But that's basically the idea of what I want to build. Right, we have assembled a bunch of hardware bits. Let me just go through what we have. We have a couple of pieces of breadboard. I've joined those together, make a nice big one. We have our ICs. So that's SN75160 and 75161. and also the 23017, which is the multiplexer, or rather the expander. I'm using a PIEEE-400 both to write the software on and also to run the test system. So that's compatible with the PIEEE-4, but because the I/O port is sideways, I've got this device which is a port expander, and that plugs into there and brings out basically two GPIO ports that we could, basically plug a hat onto. We haven't built the hat, so I've got ribbon cables, so we can extend from the ribbon cable out to that and then build our interface on that and hook it up to the Pi and test it. The nice thing about this is that this block of stuff here is LEDs, and that is going to tell us when the signals are signaling. So blinking lights, that's a good thing. Here we have a little pot of bits, so we've got switches. These are quite big chunky switches. I don't think they're going to be the ones that I'll use in the final thing. Some LEDs, some resistors, and some buzzers. Now I didn't have buzzers on the original schematic, but these will make a noise as if it was a disk drive. So I've got one for drive 0 and one for drive 1. And this is our GPIO, IEEE-488 connector, which is basically a 24-pin Centronics. Pile of loose wires and basically some link wires. And these are our two OLED displays. That is the little link resistor. In order to change the address, we need to move that resistor there from one side to the other side. Now we can do that, but I think it's going to be very fiddly, and it's not something I think I would suggest that it went into a sort of production type board. So, plus not every screen device actually has a settable address. So what I think I'm going to do is get hold of an I2C multiplexer, and these cost a few quid. It's going to cost more, but I think it will make it easier to use, or at least easier to build. So let's get on with it. So I've laid out the breadboard with the components, or at least most of the components. This is the 160, this is the 161, and this is the 23017. Now I've wired them up so that this is the 5 volts line, runs down here, the red one on the outside, both sides, although I don't think I need 5 volts down here. And in the middle, this is the 3.3 volt line. So these two ICs are wired up to the 5 volts, and this one is wired up to the 3.3 volts. These are the voltage wires that go 3.3 volts, 5 volts ground, goes to the expansion card. The switches, 3 on each side, are wired up to this chip. So this side, which is drive 0, is wired up to the A side, GPA 0 to 0, 1, 2, 3, 4. So that's the activity LED, that's the buzzer. And this side, the drive 1 side, is wired up to the B port. So GPB0 is 1, 0, 1, 2, 3, 4. Now this is the error LED, and that's wired up to GPB7. So 330 ohm resistors go between here and the signal line, and the other side goes to ground. These are the buzzers. That's just a power light. It goes to 3.3 volts through, again, 330 ohms. The OLEDs, I've wired up the 0 side. The serial clock and serial data are shared with the serial clock and serial data for this. They don't yet go out to the GPIO board, but they will. I haven't yet put any of the data signals in for that, but what we can do is we can just power it up and see if the voltage rails light up, and if I guess the LEDs are in the right way round. So power light comes on. That's a very good sign. Nothing else is going to happen because nothing else is programmed, and the Pi has to boot into PiOS and all that sort of stuff. These are the power lights, 5 volts, 5 volts, 3.3 volts. They basically correspond to the same layout as the pins on here. So these two, pins 2 and 3, that are lit, these are the I2C bus, which is what is going to go out to here. So turn that off. Let's add the I2C bus. What colour shall we have? We shall have green and yellow, I think, because why not? So on these, green is data and orange is clock. So is we plug the yellow one into that and the green one into that, so that at least the green is consistent. And then on this side, green is data and yellow is the clock. That's correct. So there we are. That's connected. Now I'm going to go away and write some code so that we can test these bits and see if they work. And once I've done that, then I'll set about starting to wire these up. We are going to set up I2C on this Raspberry Pi. So we need to enable it first. And for that we go to Preferences and Configuration. Interfaces, I2C, OK. And then we need to reboot the Pi in order to have it take effect. In order to use the GPIO bus, we need to install a driver for it. And there's a choice of drivers, or libraries rather. And the one that I am going to install is called PIEEE, or actually PiGPIO. It seems to read like PIGPIO. And I am following a set of instructions, so I have not done this before. It says if the initial part of the make, the compilation of pigpio.c takes 100 seconds on early model Pis. Be patient, the overall install takes just over 3 minutes. Okay. So it's downloaded and now it's making it. Oh, done. That looks like it's done it. So there is a daemon that needs to be running in the background, and we can start that. Sudo pigpiod or pigpiod. Right, in theory that is installed. After a bit of messing about and tweaking and so on, I've managed to get a small demo working. So what we've got is 3 LEDs wired up. 4th LED just goes across the voltage lines. 6 switches and 2 buzzers and one of the 2 OLEDs. And if I run the program, what will happen is the lights will come on. It will wait for me to press one of the buttons, any one of the buttons, and then it will beep both buzzers and turn everything off. So the lights have all come on. There we go, wasn't that exciting? This is as far as I'm going to get it this week, I think. So let me walk you through what I have done. Okay, on the hardware we've got, as before, the I/O expander, which is controlling the buttons and the LEDs and the buzzers. And then we've got the OLEDs, which are controlled by the I2C bus, which also goes to this. And we had that working the other day. And the IEEE-488 stuff is now wired up. So we're using pretty much most of the GPIO lines. The data bus is this one, which basically goes to this end of the connector. So on the LEDs it's going to be these ones that are lighting up for that. And the control lines are going to this middle section. And there are a couple of other control lines for these two ICs, which are basically to determine whether it's reading or writing, and to set the chips up accordingly. That's not actually an IEEE signal. That's a chip control signal. And then this side of those chips goes to the IEEE-488 connector, which I had to wire up like this because it wouldn't actually fit on a piece of breadboard. The pin size is not right, or rather the gap between the pins is not the same as the gap between the holes on the breadboard. So I had to wire it up directly, and that then goes off to the mini PET. So that's the hardware. It is actually pretty straightforward, basically 3 chips and a load of wires. The IEEE just goes into the back of the mini PET through this little IEEE to edge connector adapter, because IEEE to edge connector cables are pretty much impossible to find. And the scope is just monitoring the ATN and IFC lines, because that's what I have been messing with. And then in the code I've written some IEEE management functions, really. So basically I've just defined which pins the data lines are, which pins the I/O lines are, and these are the 2 control lines for the ICs. There is a third control line which I had put in to start with, but realistically that's just wired up to 5 volts, because this machine is never going to be a bus controller. It's always going to be a device, and so we don't actually need to control this. And then there is a bunch of initialization, just sets up the pins, whether they're inputs or outputs. So I've got this set up here. The OLED panel's not working. Don't worry about that, it's just not programmed. We can run this program on here, and we can go into the PET and we can type load $8 standard directory listing command. No, wrong. So let's try this again. We can type load $, close quotes, $8, and off it will go, and it will fetch the directory, and you saw the little yellow light came on for drive 0. And there's our directory listing. It's an entirely fake directory listing at the moment, but there it is. And because this is emulating a dual drive system, we can also say load $1, $8, which will get us the directory listing for drive 1, and you'll see the drive 1 light comes on. It's the same directory listing, but there you go. Now I think for drive 1 that's supposed to say 1, but I haven't actually got it to do that at the moment. And I can also get the command channel and bring back the error message. And there we are. It says 73 PIEEE-488 version 0.1 test 00,00,0. Now, if you're used to a C64, you'll only see those two numbers, but on a dual drive, you get the extra digit coming back, which is the drive number. And that also comes back on an SFD 1001. The one thing I haven't been able to make it do at the moment is if I type dir, it times out for some reason. And you can see on the debug output here, it might just be simply because I'm logging absolutely everything that happens. But this is the directory listing that it's supposed to be returning, and it goes into the comms mode. It sets the first character, and then it sits there waiting for the handshake, and the PET has timed out. Now, I don't quite know why the timing seems to be different when you do dir as opposed to load $8. It seems to send the same stuff backwards and forwards. So if you happen to know why dir should behave differently to load $8, and of course the drive light is stuck on now, but that's simply because we haven't programmed any timeouts or anything in that. It's literally just doing a few test routines and proof of concept stuff. So that's as far as we've got. I think the next step is going to be to firm up the hardware and possibly put it onto a PCB. I've got this multiplexer to handle 2 screens, but I think in the PCB version of it, I'm probably just going to have only one OLED screen. I don't know that 2 is really necessary, to be honest, and I think the amount of information that we need can be conveyed probably on one screen, but I'm willing to be swayed on that. It's also, I mean, it's to have one screen is cheaper and means you don't need that. If you had 2 screens, of course, you could possibly change the address on this if you're good at micro soldering or soldering little tiny surface mount components, but it's probably easier without. I may go to 4 buttons on each side, up, down, select, and possibly an eject button. I don't know, are there any other buttons that I need to have? We've got plenty of I/O lines to put buttons on if we need more buttons, but because this is going to be a Pi hat, no, I can't really show you that. Because it's going to be a Pi hat, I've got a Raspberry Pi 4 here. This is the one it's going to sit on. We've only got basically this area here. And that's where the connector is going to sit. Chips, OLED screen. This is really the edge of the case because we need to be able to plug in the power. At the back we need to be able to plug in the SD card. So we could expand in that direction really, but that's about the only direction we could expand it. So I'm thinking, and there's going to be space for, we've got 3 chips. Space for 3 chips and some headers. I don't think we're actually going to get the buttons on here. At least not all of the buttons for drive A and for drive 0 and for drive 1. So I think I'm going to basically put the buttons onto a little daughter board, have a little flexi wire come out, and have basically the buttons will screw to the case. And the OLED will screw to the case, and there'll just be headers to the board. I think that seems to me to be the sort of elegant solution. Anyway, tell me what you think. Thank you for watching, and thank you for the 500 subs. Yay! Please sub more, please like, please do all that stuff. Tell your friends, tell your enemies, tell anybody. and watch that video up there, and see you next time. Bye bye. The Tynemouth minstrel blah, blah, blah.